Good day and welcome. We are going to check out the International Performance Measurement and Verification Protocol. We're going to look at some of the calculations that are involved behind it and the logic. All right, let's get straight into it. So this protocol is all about savings and comparisons. Savings and comparisons in the sense that we're usually looking at energy conservation measures. These energy conservation measures are to be, put into scrutiny to see if they were effective or not, right? So we have a past without the energy conservation and the present with the energy conservation, which gives us the capacity to make comparisons, right, through time. But we can also make comparisons between systems, right? The system that was installed before and the system that was installed after, right? So we can go ahead and measure how much we're saving. This gives us to understand really with comparison in the right way, we can feel the correct impact of the savings, right? There's different methods. One is normalization, right? Another one is cost avoidance. We'll be looking into that. All right, so energy models. What is this about? Energy models is the foundation of the calculations because the energy models are going to represent a relation between some sort of independent variable and a dependent variable. And it'll give us a formula, right? A model that we can use uh, in different scenarios. For example, we're going to check that out. We usually we've been looking at linear regressions, right? Which is a simpler way of understanding this. We have an x variable, which is at the bottom. We have a y variable, which is a dependent variable, which is usually our energy use. We plot it. We got a line of best fit, and that line of best fit can be expressed as y equals mx plus b, right? In the sense that every line has its expression in this form. So y, if we look at it, the y is our energy use, the m is our rate or our slope, the x is our independent variable, which is dynamic, right, because it goes changing, and the plus b is our what we would call our base energy, right, that is usually not affected by x. In most cases, sometimes it's just lighting, right? It's not affected by weather pattern or phenomena. Uh, so creating energy models via linear regression is what we do. Uh, and we have two types of savings, right? We have avoided energy use and we have normalization, right? Both of them use these energy models to create these lines, right? But they are not exactly the same thing. If we start to look at cost avoidance and normalization, cost avoidance seems to be something that we use for uh, month to month scenario, could be for quick comparison, could be a moment where we have lack of data, or not only lack of data, but let's just say we implemented an energy conservation measure a month ago. There's not too much data to work with, but there is data to work with, even though it's not too much. And that's where we'd go with the cost avoidance, right? Normalization uses a more time span, also like a year of data. We'll look into this. So the cost avoidance calculation is rather simple. It's on the easier end of things, uh, and usually we can understand it best by seeing a bill, an actual bill, uh, versus a bill that came in, in the past. That bill that came in the past would be expressed as our base energy model, right? Which is that y equals mx plus b, which is going to represent the linear regression of our pre energy conservation measure. And then our new energy conservation measure, we wouldn't have a line, but we would have this information, right? Here's an example, right? If you look at For example, if we installed an energy conservation measure a month ago, we're looking at the effects it had on the bill. We're going to know how many cooling degree days we had or heating degree days by a temperature calculation, and our consumption will be directly on our bill, right? So from this, we have enough data to insert in our base linear regression. Don't forget our base linear regression, y equals mx plus b. We just put in that 995 cooling degree days into our base regression, and we can see how much it consumed, right? And here on the image, you can see what this cost avoidance is. It's a comparison of a reporting period, right? And you can see what it visually looks like on a graph. This is different than normalization. Normalization, here we have two energy models. Both these energy models represent before and after the energy conservation measure was implemented. One is the old system, one is the new system. And usually, like I said, we have at least a year of data for each system for this. For normalization, if you check it out on this graph, we can see the old system is in red at the top, and the new system is in a purple blue line. And this purple blue line shows the savings, right? As we compare one energy model with another, and it's normalized in its base. What normalizes here is the independent factor that makes everything the x value, heating degree days. So we put both models under the same conditions, which normalizes the situation, and we can get a better picture of energy use, right? Uh, Basically, we have those two forms of savings, and we've also understood where the logic comes for these lines, right? Which is our linear regression models, and how we can use these linear regression models in different contexts to compare and understand our savings in a more profound way. So I'd say thank you for your attention. Have a good day. Bye.